Hello everyone, this is Vishnu V. Gobi, Assistant Professor, MPC CET Pyramid. Today we are discussing a topic from VLSA. The topic is stick diagram and layout design of Cmos circuits. So in this topic, first we will discuss about the what is stick diagram and what are the layout designs in VLSI. So the stick diagram is a pictorial representation of CMOS circuits. So the circuit is distinguished in stick diagram based on the different colors. In stick diagram, we can get the exact placement of or the number of components used in the circuits. Easily understand the Pmos and the Nmos used in the circuits, and we need to easily calculate the number of components in the circuit. But one of the main thing of stick diagram is stick diagram cannot give any size of these components or size of these layers. So we can get the exact size and area of the circuit is from layout design. So layout design is used for fabricating ICs or fabricating the circuits into IC chip. So in order to make the IC chip, we need exact size of each layers. That can done by or getting from layout designs. So there are two types of layouts design rules, that is lambda based design rules and micron based design rules. In micron based design rule, we can two types, that is micron based and lambda based. So in the micron based design rule, so the entire layers size are predefined or standard. So in industry, now we are using in micron based design rule in IC fabrication. This is a industry standard. But in lambda based design rule, we can scale the each layers by lambda value. But in micron base, all terms are standard. So now we can make a table for different colors of stick diagram and what are the size of layouts in VLSI. After that, we can make the circuits design and the circuits and the stick diagram and the layout designs. So we will start from conclusion or the what are the things begins in the layout and the stick diagram. We can make it a table. So it is a layer or layer name. So this is what is the color we are denoting, and what about in stick diagram, and next one is layout design or mask layout encoding for lambda based design rule. This is the mask layout encoding for micron based design rule. So there are a number of layers. First one is N diffusion. Next one is P diffusion. So next one is polysilicon. So this is the main 3 layers. So in this N diffusion we can use it by or denote by green color. P diffusion is yellow and the polysilicon is red. So in this stick diagram we can make it a sticks. So sticks like green. So this one is yellow, this one is red. But in our mask layout we can make it like this. So mask like this. So this is a green for N diffusion. So mark like this. We can make it for also for the micron based. Also we can make a for the P diffusion. This is a mask like this. So we can dash like this. Same dash layout or dash style. So in this we can make the size in this one is 2 lambda. So this one is also 2 lambda. In this is 3 micrometer or micron. Based case this 3 micrometer. So this one is also 3. So the distance between this is 3 lambda. This one is 2.5 micrometer. In between the diffusions. So now we can make a P diffuse polysilicon. This is our polysilicon. So dash opposite to the diffusions. So for understanding the distance between the polysilicon, I am writing one more polysilicon. So the size of the polysilicon is 2 lambda. In lambda case, in micron based it is also 2 micrometer, and for Cmos it is 2.5 micrometer. This is for Nmos. Also we can make the distance between the polysilicon. So this is distance between, that is 2 lambda. So from any polysilicon, this is P diffusion to polysilicon, that is 1 lambda. Also between the N diffusion and the polysilicon is also 1 lambda only. So in between any diffusion, P or N diffusion to polysilicon, 1 micrometer for Nmos, 1.5 micrometer for Pmos. So we can also make in between polysilicon in micron based. This is 3 for PMOS and 2 for NMOS. 3 for PMOS and 2 for NMOS. So now we can make the metal. So metal 1 and metal 2. So that is blue. So we can make the blue like this. So in this we can make this the metal symbol like this, metal 1 and 2 is denoting for the micron based. So in this the distance between the polysilicon and metal is 2 lambda. Now between the metal to our polysilicon is also 2 micrometer. Also we can make to another metal, that is 2 micrometer, and this one is 3 lambda to another metal. So another metal, this is our another metal 1 or 2. Now we can make the distance between two polysilicon in the micron based design rule. So in between two polysilicon, this is our distance between here. So that is 2 micrometer. In between two polysilicon, the gap between the two polysilicon is 2 micrometer. So now we are moving to the next one is metal 3 and 4, that is also denoted by blue. So the symbol is like this. The section lines are in horizontal, so the size are varied. Also this one is 4 lambda, this one is 4 greater, this one is 3 lambda. Also this one is 2.5 micrometer. So this one is 4 lambda, this is 3 micrometer. So in between to the another metal, in between to the another metal, and in between a metal in the micron based design rule, this is 3 micrometer in between. So in between this is 4 lambda. So one more layer is here for the NMOS depletion layer and the NMOS enhancement, and also for the PMOS. So this one is for the stick diagram and the layout design of Cmos circuits. So stick diagram is distinguished by different colors. So one of the main part is we need to remember this size and the distance between each layers. So we can make a conclusion that is the mask for N diffusion is making by green. So this one is green. For the lambda base, that is 2 lambda, this one is 3 lambda. So between to P diffusion is yellow. Between N and P, that is 3 lambda, this is 2.5 micrometer. So next one is polysilicon, that is red, that is denoted by 2 lambda and it is also 2 micrometer. So in between the polysilicon is 2 lambda. For this one is going to be 2 for NMOS, 3 for PMOS. Also the polysilicon is coming to between diffusion layers. So we can make the N or P, the distance is 1 lambda. For micron waste, for PMOS 1.5 and NMOS for 1 micrometer only. Also that the distance between two polysilicon is 2 micrometer. Also in this, for the thickness of polysilicon, for NMOS is 2 micrometer and for PMOS is 2.5 micrometer. So there is some variation for NMOS and PMOS in micron based design rule, but lambda it's exactly same values. So moving to the metal 1 and 2. So the thickness is 3 lambda, for micron 2.5. The distance is same, 2 lambda and 2 micrometer. So in between the metal 1 to the another metal 1 is 3 lambda. In micron, that is 2.5 micrometer. Also metal 3 and 4. So metal 3 and 4, the thickness is 4 lambda and in micron that is 3 micrometer. So 3 is same like this between metal 3 and metal 4, that is 3 micrometer and this one is 4 lambda. So we can make a next one is contact cut. So that is denoted by black color. So this is our contact cut. In this mask layout, for same for this, for like this one, for fully blacked box or crossed box. For same as for the lambda and micron based layouts. So we can make a one more thing, that is how to make the NMOS depletion layer and the NMOS enhancement, and also for the PMOS depletion and the PMOS enhancement. So we can make the continuation of the table, that is layer. So layer and the mask in the lambda based design rule. Mask in the lambda based design rule. That is, first one is NMOS depletion in bracket implantation. So we can make this by, so we can make a transistor is by 4 NMOS, that is a one is green, diffusion is green, and the polysilicon is crossing. So we can get the NMOS depletion mode by making a implant between this. So this one is 2 lambda into 2 lambda, and the square of the implant is 6 lambda into 6 lambda with the dotted yellow lines. Also for the PMOS, sorry, for the NMOS enhancement type transistor, we can make this one same like this. So we can make the green, So we can make the red. So there is no implant is here. The channel is created by the gate voltage. So this is the NMOS enhancement type. So we can make the same thing to the PMOS depletion. PMOS depletion is, we can change this one by layer is changed to yellow, and for enhancement is same like this. Layer is, the diffusion layer is yellow, and the polysilicon like this. The size are same. So this one is like this. So this is 6 lambda into 6 lambda implant. So this one is 2 lambda into 2 lambda. This is same as that of 2 lambda into 2 lambda. 2 lambda for this. This is also a 2 lambda into 2 lambda. We can also make one of the contact cut. So consider this. So this is all how to make the contact cut. So I am making a one more example for the contact cut. So making a transistor in this area. So this is a one transistor and this one is another transistor. So after that I am creating the contact cut. So this is our contact cut. So in between the polysilicon to the contact cut is 2 lambda. Also that this one is 2 lambda into 2 lambda. And one more thing is, the between the transistor to the another one is 2 lambda. So this is all about the general view of or outer view of the layouts and color representation in stick diagram, and the what are the sizes in lambda based and micron based design rule. So now we can make the some more examples. We can start from the NOT gate, Cmos NOT gate. So Cmos NOT gate is like this. So this is our diagram. This is our VDD and this is our Vout. This is our Vin. So this is NMOS and this one is PMOS. So we can make this by how to write the stick diagram and how to make the layouts. So the sequence of this design is first starting from circuit or equation. If you are giving any equation, first we will make the circuit, and after that we will make the stick diagram. We will make the stick diagram into this, and we will start from the circuit or equation and then move into stick diagram of each parts, and then we will create the layout. So in this layout we can make the layout from the stick diagram. So we can start like this circuit diagram or equation, then move into stick diagram and then move into layout. So if you are getting an equation, first we will convert into circuit, then making the stick diagram and making the layout. So First we will start from the stick diagram. This is our stick diagram. So in this stick diagram there is a first thing is he will draw the VDD and ground, that is blue. So then after that we can make the Pmos and Nmos transistor. So Pmos is, this is, look into this one. So this is source and drain, this is source and drain. So think about this. Pmos source is connected to VDD and Nmos source is connected to ground for every Cmos circuits. So first we will draw the VDD and ground. So the stick diagram is drawing in between the VDD and ground. So we can make the first thing is we can make the Pmos transistor. So Pmos transistor, that is yellow. And next one is we can make the Nmos. So in between there is a metal is here. So we can make the metal. So next one is we can make the transistor. So transistor is making by polysilicon. So this gate is connecting to this gate. So simultaneously we can connect this one. So we can create the Pmos, we can create the Nmos also. So next one is we can make the terminal of the gate. So this one is starting from a metal. So this is our diagram. Now we can make the contact. So this one is a contact, that is based by the black color. This is also a contact, this is contact, this is contact, this is contact. So we can make the another one metal from the output to output terminal. Okay, also make the contact. So this is the stick diagram of Cmos NOT gate. Now we can make the layout. So in this layout, we can make the first one is metal 1. So this is our metal 1. So I can write the metal 1. So metal 1 is like this. So this one is also metal, that is ground connection. This is VDD, this is ground. So next one is we can start the polysilicon and we can make the Nmos. So this is for P diffusion, this is for N diffusion. So we can make the contact is make connected. So the next one is we can make the metal. So this is our metal, just touching the each layer. So we can also by making the metal 1. So this is also another metal is in the output. So this is also a metal. So we can make the contact. So from this we can make the polysilicon. I think the picture is going to small. So we can make enough space between this. So just crossing the point, we can get the layout of this one. So we can make the one of the another metal, this is the input. So making the contact. So this is our V in, this is our V out, this is V out, this is V in. So this is how we can make the circuit diagram of Cmos circuit diagram and making to the stick diagram and making to the layout from the stick diagram. Also, if you are thinking about the lambda based design rule, you can make the or assign the each layers. For this is 3 lambda. Also, in between metal and the polysilicon is 2 lambda, and the thickness of this one is 2 lambda. Also this one is 3 lambda, this one is 3 lambda. Also this one metal to polysilicon to metal is also 2 lambda. We can make this all terms. This one is 2 lambda conductor. Also we can make the all theorems in this, and also make the polysilicon, and the all things need to be defined if you are using lambda based design rule. If you are using the micron based design rule, we can use this one is 3 micrometer for the standard one, that is based on the conclusion what in the discussed earlier in the starting of this topic. So this is the CMOS NOT gate. So now we can make the some of the circuits. So how to write the or draw the or design the CMOS circuits, and how to draw the stick diagram and the layout. So moving to the topic, how to design the CMOS circuits. So in this we can make a idea, that is NMOS transistor. If the equation become contain plus operator, that is parallel. If you are making the equation contain multiplication, this is series. So we can make the conclusion for PMOS. If the equation contain multiplication, that is parallel, just opposite to this one. The plus one is happens, that is series. This is our assumption. So now we can make the NOR gate. So the equation become y is equal to a plus b the whole bar. So in this case we can make the circuit by the first one is this is our VDD, this is our ground. So when the pull-up network, say consider this a middle point, the above point is called pull-up network. This only contain PMOS. This one is pull-down network. It's only contain NMOS transistors. So there is a plus operator is here. So this one is the area for PMOS. So if a plus operator is here, so the PMOS is in series. So we can write PMOS is in series. So the input is A and B. This is our middle part. We can take the output. This is our output Y. So we can make the plus operator here. So this is the area for NMOS. In this area does not contain PMOS, only contain NMOS. transistors. So the plus is here, so the plus is parallel, so the NMOS is parallel. So this is the parallel condition to ground. This is A and this is B. So this is the CMOS circuits. Now we can make the stick diagram. So moving to the stick diagram. Of NOT gate, we can make by first we will allocate much space for drawing the diagram in between VDD and ground. So we can make the VDD and ground, make much space between this VDD and ground. So now we can make, already discussed, this one is source, this one is source, this one is drain, this one is source for this one is drain. So we can make this by just forming the layers. So we can make this by, there is a yellow for P and there is a green for NMOS. So we can think about this. So this one is source, this one is source, this is drain, drain. We can make the starting from PMOS, the PMOS one source is connecting to the VCC. So this is one PMOS. So we can make the two transistors. So one of the transistor is connecting to VCC, that means VDD. So source is connecting to VDD. This is our drain. So this drain is connected to the other source. So this drain is connecting to like this, connecting to the NMOS. So we will start to making the NMOS. So this one source is connecting to ground. So create the two transistors. So one of the source is connecting to ground. So this one is also connecting to ground. So the drain is simultaneously connecting. So we can make the simultaneous connection of this. So this one is connecting to our D. So we can make the output. Also we can note that the A is connecting to this A. So we can make direct connection. So we can make direct connection because the B is directly connected to the one PMOS to one NMOS, one PMOS to one NMOS. So A are same values, we are directly connecting. So we can make finally the contact. This is our contact part. Also we can make the another contact like this. This is A and this is B. So this is the stick diagram of NOR gate. So now we can make the layout. So in this way layout we can draw simply from the stick diagram. This is our VDD. So we can make the ground. So we can start from the metal part. This is our metal part. So now this we can make some much area. So we can make the P diffusion by yellow. Also we can make this by say vertical arrows. So we can make the diffusions to the polysilicon. This is our diagram. So we can make the metal part. So this is one of the metal is coming. So one of the metal is taking from this. This is directly connecting to the output part. So next one is connecting a another one. It's another metal. This is also for another metal for B. Also there is a connection to our VDD and ground. So this is the diagram. So we can make the contact. Also that there is a connection of this one to ground. This is our another contact. So we can make the sizing by lambda, which one we are using. Whenever we are using lambda, we can use the separation between the each layer and the size of each layer demanded by from the table. Also we can make the distance between the polysilicon and the metal also, and the thickness of all this. The thickness and also the distance between each layer is very important. So whenever we are using the micron based, we can make this one by micron based design rule. That is very important. So this one is VDD. This one is A and this one is B. So this one is our V out. Also we can make the NAND gate. NAND gate. In this NAND gate, we can make the assumption Cmos plus, that is we can already defined in the circuit part of the NOR gate. So plus is happens, that is parallel. Multiplication is happen, that is series. Pmos is just opposite to the Nmos. Multiplication happens, that is parallel. Plus is happens for the series. So we can write the NAND gate, that is y is equal to AB the whole bar. So we can make this VDD and ground. So this is our middle point. This pull up part and this pull down part. Pull up part only contain PMOS, pull down only contain NMOS. So pull up part, whenever the pull up part is a multiplication is parallel one. So we can write the parallel. So this is Pmos. We can write this one is A and B. This is our middle part. We can take the output. So AB is here, the NMOS, multiplication is here, so the NMOS is series. So we can write series. So this is our ground part. This is our A and B. We can also write the stick diagram of this one. Stick diagram of NAND gate. So we can make the blue for metal. This is VDD and this one is ground. So we can make the PMOS and NMOS is here. So making the demarcation line. This is our demarcation line, brown dotted lines. So the next one is we can make the circuit. This is source, this is source. The two sources are connected to VDD and this one is drain. So we can make this one by, first we will write the PMOS. The next one is we can make green for NMOS, yellow for PMOS, green for NMOS. So we can make the terminals. So this one is connecting to, this one is making the theorem. So there is a source is here. So source is connecting to the metal. So one of the another is connecting to metal. So this is the drain bar. We can take the drain bar to the output. So we can also make the A, this one for the B. So we can make the A is here. So we can write this source drain, then source drain. So we can make the one of the source. I think this is B. B's source is connecting to ground. So the next one is, this is source, this is drain, this is source, this is drain. So the drain is connecting to the output terminal. So somewhat like this. So this is our circuit diagram. So we can make the marking, contact. This is our contact. Also we can make the terminals of the inputs. This for A and this for V. This is our V out. So we can also make the layout. Make the layout. So first we will start from the metal one. This is our metal one. Next one is for the ground, metal 2. This is our VDD and this one is ground. So now we can make the P diffusion and N diffusion. So now we can make the polysilicon. So our polysilicon, another polysilicon. So now we can make the metal part. This is our one of the metal part. I think we are using the metal one only. We can use 3 and 4. So we can connect this one is also to the metal. So also we can make the one of the term to this terminal. We can make this way simply from the stick diagram. We cannot get any confusions. The stick diagram is correct. You will get the correct layout part. This is our diagram. We can make the final contact. We can make the sizing based on the which layout design we are using. Whenever we are using lambda, we can use the lambda sizing. So whenever we are using micron based, you can make the micron based sizing and the spacing. So now we can make some simple examples. How to make the XOR gate based on Cmos circuits. So y is equal to, we can write a bar b plus ab bar. Already discussed NOT gate, NOR gate, and the NAND gate contain a bar output in this equation. A final bar is here. So in this CMOS circuit, the output is in the bar condition or inverter condition. So if you are using any circuits or implementing any circuits in this, we can use the inverter at the output stage for normal output. So in this case there is no bar output, so we can apply the De Morgan's theorem. So double bar is here, so we can make this one by a bar b whole bar dot ab bar whole bar whole bar. The De Morgan's theorem is if AB the whole bar is happened, that is a bar plus b bar. You can also write a plus b the whole bar is equal to a bar dot b bar. This is De Morgan's theorem. So in order to make the circuit is balanced, we can use double bar. So if a double bar is what? A bar b plus ab bar whole bar. The whole bar is only this terms. So we can use the double bar. So now making this first term into second term, we can get this equation. Apply this one, we can get this. So also consider this. This is like this equation, a b the whole bar, a bar b the whole bar. We can rewrite a double bar dot b bar dot we can make this equation by a bar b double bar. So a into b the whole bar is equal to a bar plus b bar. So we can write a double bar plus b bar. So the equation like this, there is a whole bar is here. So we can rewrite, that is a plus b bar into a bar plus B. The whole bar is here. Don't forget this bar. So now we can write the Cmos XOR gate. So there is a VDD is here, there is a ground is here. So we can write, so there is a middle portion. So the equation contain a plus b bar into a bar plus b the whole bar. So we can write the general form. The Nmos positive is parallel, multiplication is series. For Pmos, multiplication is parallel, addition is series. So think about this. This one is the plus operator. So plus operator is Pmos is series. So this one is series. This is A and this one is B bar. So we can write like this. Also think about this. This one is, another one is this one. So this one is also series, that is A bar and B. So this one is, this equation is multiplied with this one. So multiplication is happen. This one is parallel. So we can write this like this. Also we can think about this. There is a plus operator is here. So the Nmos is parallel. So we can make the parallel one of this first equation, that is A and B bar. Now there is another one that is also in parallel one. So that is A bar and B. So there is a multiplication is here. So multiplication means this term is series with this term. So this is series to the ground. So this is our V out. This is the XOR gate. Simply we can write this from this assumption. This assumption, Nmos plus is parallel and multiplication is series, and just opposite to the Pmos is just opposite to the Nmos. Now we can write the equation for simple equation. Y is equal to AB plus C into T plus C the whole bar. So we can think about this. AB is multiplication. So there's a VDD is here, there is a ground is here. So first we will think about the AB. The multiplication is here. So we can make, that is Pmos is parallel. So this one is parallel. This one is A and B. These are parallel. So we can make this D plus C into C. So D plus C is plus 1 is series. So we can write series. This is D and E. So this is parallel. Parallel means multiplication means parallel. So we can write C. Also this term is series because plus is series with AB. So this is series. So we can write the output. So we can move to the Nmos part. Just opposite, AB is here. So AB is multiplication is here. So AB is series. So this is A, this is B. Now we can write D plus E. Again D plus E is here. So D plus C is happened. So this one is parallel. So this D and E, parallel one. So that is come to a series one. So we can make this one is series one. So we can make this one is series. So this one is C into D plus D is plus is here. Plus is parallel. So we can write like this. So like this. So this one like this. So we can make the circuit diagram like this. So this is C. So this is AB plus C plus DE. So this is one term and this is another term. So this is plus is here. Plus means parallel. So this term is parallel to this term. So we can write easily by this term is coming to this one. So we can make it parallel very easily. For explanation I am writing this in the bottom side. So now we can make the another explanation or another example, that is simple equation y is equal to AB, that is AND gate. So in this AND gate we can apply the De Morgan's theorem because there is no bar output. So we can apply De Morgan's AB double bar, that is equal to A bar plus B bar whole bar. So we can make this. So there is a VDD is here, there is a ground is here. So we can make the A bar plus B bar. So plus operator is coming. So plus operator is coming. The upper part is, pull up part is Pmos. The plus is coming, that is series 1. So we can make the series of Pmos. It's because plus operator, that is A bar and B bar. So we can make the output. So now plus is coming, so the NMOS is parallel one. So this is A bar and this is B bar. So we can get the answer. This is why you have to make the output. Also we can make the circuit also by another one. So how to make this circuit to another one? So look into this circuit diagram. So this one is like A bar plus B bar is here. So when we need to make this circuit into another one, what happen? We need to make this AB is here. So AB is here. So what happen? The output is going to be the opposite one. Like this NAND gate. The output of the NAND gate, we are applying NAND gate is, we will get the AND gate only. But in this case we are applying the NOT inputs, so we will get the output is like A bar plus B bar whole bar. Now I am giving a last example, that is y is equal to A B bar plus C. So we can, there is no bar output, so we will make two Cmos circuits making two bar, then apply the De Morgan's. So AB bar whole bar into C bar whole bar. So we can further make this one is A bar plus B into C bar whole bar. we can make this by simply starting from VDD and ground. So there is a +1 is here. So plus is happens, the Pmos is series. So the Pmos is series. This is A bar and this is B. So now make the C bar is multiplied with theorem. So multiplication is happened. This one is parallel. So this one is parallel coming C bar. So this is connected into VDD. So coming to this side. So this is our V out. Coming to the Nmos part, that is A bar plus B. So the plus is happens, that is parallel. So we can make this one is parallel. So this is A bar and this is B. So the C bar is multiplied with this theorem. So the multiplication is happened. This one is series. So C bar is series. We can make this circuit simply by De Morgan's theorem for the non-inverted outputs. So whenever there is no bar is here, we can apply double bar and make De Morgan's and make the circuits. So also think about this. So consider this upper part, pull apart. So if your pull apart is the element is series, it's going to be parallel. It's going to be a parallel one, it's going to be series. So just opposite to PMOS to the NMOS in the pull down network. This is why we can make the circuit from equation. Then we will make the circuit and it's going to be a stick diagram and it's moving to layout. We can simply making the layout for IC design. This is Vishnu V. Gobi signing off. Jai Hind.